you get attractive complexity. You can do it really, really quickly, but the question is at what cost, right? And this comes back to your question when you were asking, is there a chance that after doing it with 20 tables, you never find it? And yes, there is a chance, and we can quantify that chance. So what we're looking for the false negative rate, or the miss rate of the LSH. And what it means, what the miss rate means, is I have two documents A and B. They're close by. They're almost identical. They're different by maybe a couple of words. So what is the probability that they will not collide in any of my L hash tables? So what's the probability that I never find them in the same bucket? And that we can figure out, right? So that happens if none of the L hash codes for the two documents are exactly the same. So if none of the L hash codes match, then I will never see A and B in the same bucket of some hash table, so there will be a miss. Now, what is the probability that none of the hash tables for A and B match? Now, the way I'm generating the hash codes is I'm cutting the space with random hyperplanes. So the different sets of hyperplanes are completely independent of each other, and they're also generated in the same exact way. So the hash codes are independent of each other across different hash tables, and they're also identically distributed because I'm generating them according to the same random process. So the hash codes are IID. Now, since they're independent, I can turn that statement, none of the hash codes match. This means every one of the L hash codes is different, and that just becomes a product over L different hash codes that I generate for each of the L hash tables. The probability that the ith hash code for A is different from the ith hash code for B. Okay? So now I need to estimate that. What is the probability that the ith hash code for A is different for B? But before I do that, I'm going to simplify this product a bit. Not only are they independent, they're also identically distributed. So instead of doing the product, I can just take this probability that the ith hash code is not the same and raise it to the power L, because every hash code is independent of each other and it's identically distributed. So it's just the probability that the hash code of A is not the same that the hash code as the hash code of B raised to the power L. So I have L independent events. Now, what is the probability that a hash code is different? Remember, a hash code is a sequence of k bits. And for the hash code of A to be different from the hash code of B, it's enough to have one bit that is different. So if any one of the k bits is different between the two hash codes, they will not match. Right? So the probability that the hash codes are not equal means that any of the k bits are different. Right? And another way to write this is any of the k bits are different if it's not the case that all k bits are the same. Right? I'm just doing logical negation here. So the probability that any bit is different is 1 minus the probability that all bits are the same. And I'm still raising it to the power L because I'm repeating it L times for L different tables. So I have 1 minus the probability that all bits in a hash code are the same. And now I play the same trick. The individual bits are independent. Why? Because they're based on separate hyperplanes, which I generate completely randomly. And they're also identically distributed because I'm sampling the hyperplanes from the same random number generator. So I can rewrite that as follows. The probability that all k bits are the same is the probability that one bit is the same raised to the power of k. And 1 minus that quantity is the probability that any one of the k bits is different. So that is my final form, and usually what you do is you represent this event, the probability that some bit is the same for two different points A and B. You call it P, which is a parameter of the LSH, and we'll talk about where that comes from. So overall form is just going to be 1 minus P to the K. So P to the K is the probability that all K bits are the same. 1 minus that, probability that at least one of them is different, raised to the L power. It is repeated L times in a row. So that is the probability that A and B will never land in the same hash table bucket if I generate k-bit hash codes and repeat the process L times. Okay? Now, you can make a very similar argument for the false positive rate. So what's a false positive rate? False positive rate, that's, so in terms of the previous slide, that's one of the documents that you didn't want to have in the hash buckets, but it still ended up being in that hash bucket by accident. So you don't want A and B to collide. What is the probability that they collide by accident? The probability that they collide by accident is the probability that at least one of the L hash codes is the same, and that means that all the K bits in that one hash code are exactly the same. So you can work it out. It works out to about that, 1 minus Q to the K raised to the power L. So you have a parameter Q here. Typically you have P and Q are different because P is a parameter. It's the probability that they have the same bit, assuming that they are in fact near duplicates. And Q is a parameter that they have the same bit, assuming they're not near duplicates. So here A and B are negatives. You don't want them in the same in the same bucket. So Q is the probability that they have the same bit. Now, where do we get P and Q? And it turns out for LSH, the way we've described it, you can figure out what P and Q are going to be fairly simply, right? So I'm going to take my space from the previous slide, sort of, and look at it from the side. Okay, so I have two dimensions, dog and cat, and let's say I have two documents. They're landing somewhere. So this is document A and document B. And what I'm interested in is I'm interested in the probability that one of the bits for A and B is going to be the same, or that one of the bits is going to be different. They're related events. Now, think about how am I assigning the bits? I'm assigning the bits based on the hyperplanes. So what I'm going to do is I take a hyperplane, I cut through that space, and then the two documents are going to end up having the same bit if they happen to be on the same side of that hyperplane, and they'll have different bits in one event, only if the hyperplane cuts between them, right? So if I have a hyperplane that happens to cut between A and B, then B is going to have bit 1 and A is going to have bit 0. So the probability that A and B have a different bit is just the probability that a hyperplane lands between them. Now, what is the probability that a hyperplane falls between two vectors A and B? And that you can compute quite easily, because think about, how am I generating these hyperplanes? I'm generating them by sampling random numbers. They're random hyperplanes. So a hyperplane is equally likely to fall anywhere in this quadrant. So the probability that it's going to cut between A and B is proportional to the angle between A and B. So this angle shaded is theta. So my probability is just going to be proportional to how big theta is with respect to the entire to the entire quadrant. Now, what is theta? A and B are documents. They're unit length vectors. I'm projecting them to a unit sphere, right? So if I take A transpose B, if I just do a dot product between A and B, when they're unit length, a dot product is just the cosine of the angle. So you can compute the angle by doing the dot product and taking the arc cosine of that. That'll just give you the angle theta. Right? So the probability that a hyperplane, a given hyperplane, a random hyperplane, is going to cut between A and B is just theta, the angle between the documents, divided by the overall angular size, which in this case is pi over 2. Right? So that's going to be the probability that two documents are separated And then you can use that to compute the probability that they have the same bit. It's just 1 minus that, right? And I'm substituting the arc cosine instead of the theta. Okay. So now you know how to relate the probability, now you know how to relate the cosine between the two data points to the probability that they will have the same bit. And then you take this same bit probability and put it into your estimates, and now you can compute the the miss rate of your LSH. You can figure out how many near duplicate pairs you will miss and how many false alarms you will have, how many false positives you will have to compare to in your buckets, and they're both dependent on that P.